All right. So hopefully everyone can see this okay. All right, I'm getting some thumbs up. That's great. Okay. Well, welcome everybody to this week's Rubin Science Assembly. My name is Sarah Greenstreet, and I am going to be leading us on a tutorial of one of the tutorial notebooks on exploring the orbital properties of near-Earth objects. But before we do that, let's see, can I get my slides to advance? Okay. So I have a couple things to run through. So for the agenda today, we're going to cover a couple announcements to start, and then we'll be going through this tutorial notebook, DP 0.3, number 5, titled Near Earth Objects. That's on GitHub here at the link. Let's see. I should probably put the link to the slides in the chat so everybody can get this. Here we go. Where's my chat? There it is. Okay. All right. So hopefully everybody has access to the slides so that you can access the links in the slides as well. Please let me know if that didn't work correctly. And so we're going to spend most of the time going through this notebook, and then there'll be time for questions throughout. Feel free to interrupt me anytime if you have a question, or we'll have some time for questions at the end as well. Okay, so a few announcements first. I saw the announcement, many of you may have as well, in the recent Rubin Digest email that went out, that there were some really great drone images that were taken by Olivier Bonin, who traveled to Chile in order to document the LSST camera arriving in mid-May. And these are available on the gallery. There's a link here. I thought for fun, whoops, that I would show just a couple of these quickly as well. There's some of them in the gallery here. So if you, where's my screen? If you just go to the gallery in this link, it will take you here. And some of these first images up here are from those drone images taken by Olivier. And there's some quite spectacular ones in here. And so I encourage you to go check these out as well, because they're pretty fun to look at. So that was one thing I thought would be fun to bring to everybody's attention. Also, another big upcoming event for us is the Rubin Community Workshop, which is going to be happening in a couple weeks here in July, on July 22nd to 26th. It's going to be at Slack this year instead of in Tucson, and there will also be virtual components as well. So the meeting website link is on this slide. Registration is still open. It was supposed to close last Friday, but it's been extended through this Friday, so June 28th, tomorrow. So if you would like to come in person and you haven't registered yet, please do that before tomorrow or by tomorrow. There is also space for in-person posters. If you want to come in person and want to present a poster, you are still welcome to be able to put in an abstract for a poster, because we still have room for posters. The talk spots are all filled, but there is room for a poster. And there's also now a venue for virtual posters. There's a link here on this slide as well, that is on the Rubin Community Forum. And so if you click on this virtual posters link here in this slide, it will take you to the community forum post that explains what these virtual posters are for the community workshop, and how to make them. Anyone is welcome to make them, and I think you can make as many as you want. And so if you want to come to the community workshop virtually and still want to have a poster to share with people, you can make one of these virtual posters to be able to let everyone see as well. Virtual registration is still open. I think will stay open through the conference, if I am not incorrect in that. Virtual registration is free, but it is mandatory in order to be able to access all of the Zoom links and the Slack space for the workshop and all of the other information that is needed to be able to participate. So if you want to attend virtually, then please make sure that you register so that you can get all of the needed information to be able to participate. And one last thing about the community workshop, the LSST Discovery Alliance this year is offering grants to help provide childcare support for people who need it in order to be able to attend the community workshop. So if you are interested in that, you can find information on those grants and how to apply on the LSST Discovery Alliance website, which is also listed on this slide. So I think those are all of the things to cover the community workshop, which is coming up in just a couple weeks. And we hope that we will be able to see all of you there. A couple other things. I think this has been mentioned the last couple different science assemblies, but we now have Spanish language DP0 tutorials that are now available as well. And if you're interested in those, there is a link here to the community forum post with information about those tutorials as well. And finally, the LSST at Europe 6 meeting is going to be happening in mid-September in La Palma. And there's a link to the meeting website here if you are interested in attending that meeting as well. Okay, so I think that is most of the announcements, the general announcements. Looking ahead at the Science Assembly schedule, next week, we will not have a Rubin Science Assembly since next Thursday is the 4th of July holiday in the US. And so there will be no Rubin Science Assembly next week. 2 weeks from now, we will be back with another tutorial, which will be given by a guest speaker, Valerio Caruba, who is on this call today. He's going to be telling us about asteroid taxonomy with DP 0.3. So please come to that tutorial to hear more about that as well. We look forward to that one. Okay, one last thing. We have been trying to make sure that we let everyone know that the Rubin Users Committee is available for giving feedback on any of the Rubin data products and the Rubin Science platform. Their charge is to gather information from the community about both the Rubin data products and the science platform. So if you have any feedback, there's a lot of information on this slide. There's a link to a Google form that they ask you to provide specific feedback to them at, and as well as other contact information. Another thing the users committee does is to be able to write reports that are sent twice a year to the Rubin operations director directly, recommending any improvements to both the Rubin data products and the Rubin Science platform. So the members of the Rubin Users Committee are listed on the slide here. And they're a really good resource if you have specific feedback on the data products in the science platform. They're a great avenue for giving feedback that can then go directly back to the project and even the Rubin operations director himself. Okay, I saw something pop up in the chat. Will there be a science engagement committee talk or poster at the community workshop? I do not know if there will be specifically or not. I think the agenda is out on the website. And so, Bob, you can go take a look through that. I think all of the details for each of the different sessions are in there.
Okay,
sorry,
I was
don't
just
know.
thinking it'd be cool to see how this has grown over the years, and and the notebooks and everything. It's just it's pretty amazing.
Yeah, absolutely. I think this year's workshop is a lot focused on the community and the science that the community is doing, and there will still be lots of participation from the project itself, but it's not quite as project heavy as it has been in years past. Douglas, I saw your hand go up.
Oh yeah, I guess a brief response to Bob. I don't know if we have anything for the Rubin community workshop, but we did have poster describing the science community science team efforts and these things at the January AAS meeting. It's an e-poster. I'll try to hunt that down and send the link.
Yeah, great. Thank you, Douglas. I also see in the chat that Sean notes that July 11th, which is when Valerio Caruba is going to be giving the tutorial on asteroid taxonomy with DP 0.3, that conflicts with the NASA Small Bodies Assessment Group meeting, which a lot of people will be at as well. So that is correct as well. Hopefully that won't diminish attendance for people who are interested in DP 0.3 too much. But you're right that there will end up being a conflict. I think the times also overlap. So, but Valerio's tutorial will be recorded as usual. And so for people who aren't able to come to the Science Assembly on the 11th, we'll make sure that the recording goes out for that as well, so that everyone will be able to watch it at a later time if they can't come. Okay, so I think that covers all of the announcements. So I'm going to go ahead and exit out of here, and then I can get my Zoom screen to cooperate. Okay, so let's start going over our tutorial here. So if you would like to follow along with the tutorial this time, you can go to data.lsst.cloud to be able to get to the Rubin Science platform. This is what the landing page should look like. On the top right corner, if you aren't logged in, you can hit the login button and be able to oh, thanks, Douglas, for putting the link to the e-poster in there. Great. Okay, so you can log in on the top right-hand corner of the Rubin Science platform. Once you've logged in, we are going to be doing one of the notebook tutorials today. So you can click on the notebooks aspect here. We are going to use the recommended weekly image. And today we're going to do a medium-sized container, since we're going to be making lots of plots for this tutorial. So we can go ahead and hit start, and that will spin up our server. And while that's happening, check the chat again. Okay, great. Conversations are happening. That's good. Okay, so the tutorial that we're going to cover today is looking at orbital properties of near-Earth objects in DP 0.3. So once this spins up, here's our landing page. If you go into your tutorial notebooks folder, in here, we're going to scroll all the way to the bottom of the list. The DP 0.3 tutorial notebooks are at the bottom here, and we're going to pick the notebook that's the second from the bottom, DP 0.3 notebook number 5, Near Earth Objects, and we'll go ahead and open up this notebook. Okay, so this notebook is really covering a beginner level introduction to near-Earth objects, or NEOs, that are in the DP 0.3 simulated catalog dataset, and also walks through illustrations and discussions of the 4 different NEO subpopulations as well, and how to make plots that can allow you to look at each of these different subpopulations individually as well, and not just the entire NEO population altogether. So in order to make all of the nice plots, we're going to do just a very quick introduction to near-Earth objects themselves. Near-Earth objects are small bodies in the solar system that are defined to have perihelion distances, which is their closest orbital distance to the sun along their orbits, that have perihelia less than 1.3 AU. So any small body in the solar system that has a perihelion less than 1.3 is a near-Earth object. And so we are going to want to extract all of the objects out of the DP0.3 catalogs that have this specific criteria in order to be just looking at the near-Earth objects, which we're focused on in this notebook. Traditionally, we also add a couple other orbital element restrictions for NEOs. Today, we're going to restrict all of our semi-major axes to less than 4 AU in order to keep the NEOs we're looking at objects that are really truly in the near-Earth region, as well as eccentricities that are less than 1, so things that are bound to the solar system. So here we're going to examine the orbital properties of the NEOs. We're going to plot the planet crossing regions that also help to define the boundaries of the 4 NEO subpopulations, which are Amors, Apollos, Attens, and Atiras. So to better understand these dynamical classes a little bit, it's helpful to remember that the Earth's orbit has a semi-major axis of 1 AU, and it's nearly circular with a very small eccentricity of 0.017. So this gives the Earth a perihelion distance of 0.983 AU and an aphelion distance of 1.017 AU. So an aphelion distance is an object's farthest distance from the sun along its orbit. And we use these parameters for the Earth, its semi-major axis, perihelion, and aphelion, in order to divide the near-Earth objects into these 4 different traditional subpopulations. And so this notebook has a written description that's very briefly describing the orbital parameters and the definitions for each of these 4 different subpopulations. But I also included a schematic diagram here, which I'll use. I think it's a little bit easier to visualize the difference between these different orbital classes. So I'm going to walk through this just very briefly. First up, we'll talk about the Amors, which are shown in orange here. I guess first I should mention this, the black circle here is representing the orbit of the Earth, which is shown by the big blue dot here. And then the Amors are one of the near-Earth object populations. These NEOs always remain farther from the sun than the Earth, so their orbits are completely exterior or outside of Earth's orbit. Next up, we have the Apollos, which are shown in blue here. These are Earth-crossing near-Earth objects that have semi-major axes larger than 1 AU. So their semi-major axes are larger than Earth's semi-major axis. So they're Earth-crossing NEOs that have average orbital sizes larger than the orbit of the Earth. Attens are very similar to Apollos. They are also Earth-crossing NEOs, but their semi-major axes are less than 1 AU. So smaller on average orbits than the Earth. And then we have the Atiras, which are pretty much the corollary to Amors. Atiras are always closer to the sun than the Earth and have orbits that are not Earth-crossing, but entirely interior to the orbit of the Earth. So those are the 4 different subpopulations. This is just a schematic example of the orbits of these different populations. And below, we're going to actually look at how to plot the boundaries of these different populations so that we can divide them up when we're actually looking at the orbital properties of the NEOs. So in order to do that, we need to be able to import some packages and define some functions. So there's only a couple of pretty familiar packages that we're going to import here. And so we need the NumPy package, we need matplotlib to make our plots, and we need pandas for looking at our data tables. And then we also need the LSST tap service so that we can be able to query the tables to get our population of NEOs. So I've done a lot of talking, but this is the actual first cell that we are going to run here. So we'll go ahead and run this and import our packages. We also have some functions that are really useful to define. In particular, these 2 here are going to calculate some of the orbital parameters that we need both for making our plots and for being able to divide up the different the NEOs into the different subpopulations. And these are orbital parameters that are not included in the MPC orb table that is part of the DP 0.3 data set. And so here we're going to define an object semi-major axis that we can calculate using a given pericenter distance and an eccentricity, using the relationship between pericenter, semi-major axis, and eccentricity. Here, we're just very simply going to define a function that calculates the semi-major axis given the perihelion distance and eccentricity. And likewise, it's also really useful to have the object's aphelion distance. So again, given an object's pericenter and eccentricity, we're going to define this function that will return an object's aphelion distance for us. Okay, we also, as I said, want to be able to have the planet crossing curves plotted on these plots that we're going to be making in this notebook. So we have two different functions here that are going to plot both the inner and the outer planet crossing curves when we are plotting in semi-major axis versus eccentricity space. And so this first function here will take a planet's perihelion distance, and it will create an array of semi-major axis values from 0.01, so very close to 0, out to that planet's perihelion distance, and then also get the corresponding eccentricity values as well. And so it will return the semi-major axis and eccentricity values for the inner planet crossing curve that we're going to need for these semi-major axis versus eccentricity plots that we're going to make. So we'll go ahead and run this cell. And then the next one is very similar. This is looking at the outer planet crossing curve. So this uses the planet's aphelion distance to create an array of semi-major axes values from that planetary aphelion distance out to our maximum semi-major axis of 4 AU, and then also gets the corresponding eccentricity values for that aphelion and those semi-major axes values, so that this will again give us the other planet crossing curve that we're going to want to be able to have for our plots here. Okay, we also want to actually be able to define the values for the pericenter and the aphelion for all of the different terrestrial planets, because we're going to be plotting all of those planet crossing curves and some of the plots down below. And so we're also going to need all of these values. And we've got some different parameters here to help make our plots look nice. So we're going to go ahead and run this cell. And now we are ready to start getting our query of all of the NEOs out of the DP 0.3 catalogs. So to do that, we first need to get an instance of the Rubin TAP service client. If you're used to working with DP 0.2, that TAP service that you need to call is just called TAP simply. The DP 0.3 solar system object catalogs are in a different TAP service called SSO TAP. And so for getting access to the DP 0.3 catalogs, we want to make sure that we have the SSO part in here as well. And then we're just going to make sure that the service actually exists after we try to get the instance of it. Okay, next, let's go ahead and do our query. So here we're going to query the DP 0.3 catalogs. We're going to join the MPC orb catalog and the SS object table. I don't think we're actually going to need the SS object table. It's mostly the MPC orb table because we're really looking at the orbital parameters here. And again, so here we're going to limit our query to objects with perihelion distances less than 1.3 AU, eccentricities less than 1, and semi-major axes less than 4 AU. And then we're going to set up our query, which is going to select a number of different parameters from the first catalog. So we're going to get the SS object ID, which is the common LSST solar system object ID, that is the same ID number that runs through all of the different DP 0.3 catalogs. We also are going to grab the MPC or Minute Planet Center designation so that if there are any known objects in here, we get their real community-wide known names. And then we're going to grab their eccentricities, perihelion distances, and we're also going to do their inclinations because we're going to look at their inclinations a little bit at the end of the notebook. So we're going to pull all these things out of the 10-year MPC orb catalog. We're going to inner join this catalog on the 10-year SS object catalog as well, where we're going to join the two catalogs on this SS object ID parameter. It's the common parameter, as I said, between all of these different catalogs. And then we want to restrict the objects that are returned in the query to things that have these perihelia eccentricity, and this is the formula for some major axes, that have values that are less than the ones that we defined up at the top here. And then once we get the query results back, we're going to put those results into a pandas data table that we're going to call unique NEOs. So this, I'm going to go ahead and run. It'll just take a few seconds. This will give us all of the near-Earth objects in the DP 0.3 catalogs that have these specific parameters. And then very quickly here, we're going to also use our calc semi-major axis and calc aphelion functions to add the semi-major axis values for all of the objects in our unique NEOs table as a new column for each of these values. So we're going to add a semi-major axis column and an aphelion column to our unique NEOs table. And then here we'll just print out the table to make sure that it looks like what we expect. Then we've got all of the parameters we wanted. So we've got the SS object ID, the MPC designation, eccentricity values, perihelia in AU, inclinations in degrees, and then we've added our calculated semi-major axes and aphelion distances in here as well that are both in AU as well. Okay, so we now have our table of NEOs. You can see at the bottom here, there's 39,470 NEOs in the DP 0.3 catalogs with these parameters that we've now extracted. So let's now go ahead and start making some plots. But before I do that, maybe I should pause briefly and ask if there are any questions about anything so far. Don't think so. Okay. For those of you who are at the Rubin Data Academy last week, I presented this notebook then, so this will be very familiar. We're just running through the same thing as before. Okay, so let's go ahead and make some plots. So the main plot that we're going to be doing, the two orbital parameters we're going to look at the most are the semi-major axis and the eccentricity for the near-Earth objects. So let's just do a very simple scatter plot of the semi-major axis versus eccentricities for all of the NEOs in our unique NEOs table. So here you can see all of the NEOs plotted here. The NEO population has this very telltale curve in it here on the right edge. This is the perihelion limit for near-Earth objects. So this is where the perihelion equal to 1.3 AU curve is. And so everything above and to the left of this, this value, this perihelion value, are the near-Earth objects. Everything to the right and below are not near-Earth objects. So this is looking at all of the NEOs together. We can also then put on here, let's see what comes next. I guess I should know what's coming next. Okay, so we can also, we've made these functions in order to be able to plot the planet crossing regions. We can also even put a curve on here that marks this perihelion of 1.3 AU boundary here. And so we're going to use these functions that we defined above to get the planet crossing curves, both the inner Earth planet crossing curve and the outer planet crossing curve. And we can do this as well for the outer edge of the NEOs here as well. And so let's go ahead and get all of those values that we'll need to be able to plot these curves on this plot up here. And then we can actually make that plot. So here we're just going to draw the Earth crossing curves, and we're going to label them on a semi-major axis versus eccentricity plot. So let me go ahead and run this, and then I can explain it potentially a little bit better. Okay, so now here we haven't plotted any of the NEOs, any of the objects from our catalog query, but here we have now put in these planet crossing curves using the functions that we defined above. And so this black curve here is the outer edge of the near Earth object population. So this is the perihelion at 1.3 AU curve. And then the blue curves here are the Earth crossing curves. So the vertical line at semi-major axis of 1 AU is the Earth semi-major axis. We also have the inner Earth crossing curve here on the left and the outer Earth crossing curve on the right. And so the amores, as I described above, are objects that are not on Earth crossing orbits. So I should say everything between these two outermost blue curves is in Earth crossing space, marking the inner and the outer boundary of Earth crossing space. So amores have orbits that are entirely outside the orbit of the Earth. Apollos are on Earth crossing orbits that have semi-major axes greater than 1, so they're to the right of the vertical line. Attens are also Earth crossing NEOs, but have semi-major axes less than 1 AU. And then there are the Atiras that have orbits entirely interior to the orbit of the Earth. I see something in the chat as well. Why 1.3 AU for the limit and pericenter of the NEOs? Yeah, so this black curve here, this is just the definition for what a near-Earth object is, as Sean is also pointing out in the chat as well. And thanks for the link there as well, Sean. It's just how NEOs are defined. Anything that has a perihelion within 1.3 AU, so is roughly in near-Earth space, is defined as a near-Earth object. Okay.
Yes, but
So,
why exactly 1.3 AU? Why not 1.5 or associating with Mars? Is there a dynamical reason for this?
I suppose it's probably close enough to being in between the Earth and Mars that if it's in between the Earth and Mars, then you can separate things that are not crossing, well, you're still crossing the orbit of Mars. But I think, well, I don't know what the actual boundary is. Let's see what Sean says. To be totally interior to Mars's orbit. I think you can still be Mars crossing in near Earth object space. But I think this particular pericenter distance is in between Earth and Mars's orbit. And so it's trying to help decipher things close to Earth's orbit from things that are a bit farther away and might still be considered main belt asteroids. I don't exactly know where the number came from for sure.
Thank you. That was helpful. I think yes, you need to find something that is in between planets, I believe. So I believe the 1.3 makes sense. Just wondering why exactly 1.3 and not 1.25 or something that was exactly in the middle between Earth and Mars. I think if there was exactly some dynamic reasons for this value, but that helps. Thank you.
Yeah. Okay, so we will actually look at some of the planet crossing objects as well down below here. So I think we are going to see, as Sean is pointing out, that some of these Apollos and Amores can actually cross the orbit of Mars as well. So let's keep going since I want to be cognizant of the time here as well. Okay, so we've plotted the boundaries here for the different NEO subpopulations or the NEO classes. And we've done a scatter plot of all of the NEOs up here. We can now actually use these boundary definitions to again make a scatter plot, but we can divide up each of the different 4 subpopulations based on their orbital parameter definitions. And so we can extract the populations, or sorry, the NEOs that belong to each of these different 4 subpopulations, which is what this cell does here, is to put each of the NEOs into one of these 4 different populations. It also then checks that when we add up all of those, that they actually equal the total number of objects we had in our table, so that everything gets assigned a subpopulation class. And now we can actually plot, we can again do a scatter plot, but we're going to divide them up into these 4 different subpopulations. So we'll plot each of the 4 populations separately on this one plot. And we're going to include the planet crossing lines, the curves that divide up these different populations. And so here, we've now combined the above 2 plots, essentially. We've still got our curves on here, and now each of the different NEO populations we've split up into different populations, I guess, and so they're each a different color now on this diagram as well. So since we've also extracted them each individually, we could plot any one of these individually on this plot as well. Okay, so since looking at this plot, scatter plots are often pretty difficult to tell how many points are actually potentially stacked up on top of each other. And so what we can do in order to help better see the density of points in the semi-major axis versus eccentricity scatter plot is that we can use the hex spin plotting function, which will give us a 2-dimensional histogram that's going to bin up all of those points and represent them as hexagons and color code them based on the number of points that are in each of those different bins. So we're going to take this same plot here. Here we're going to put all of the NEOs together. So we're not going to do the different subpopulations individually here. We're just going to plot all of the NEOs. We've still got our boundaries listed here so that we know where the different subpopulations are. But now we've got this 2-dimensional histogram here that shows us the density of the points in the NEO population. And so purple is where there's a low density of points. You can see in the Atiras, there's only a handful of them in the catalogs here, since they're a very rare, sparse population. And so there aren't very many points over here, but you can see piled up kind of on the edge of the Amors and the Apollos here, and certainly in the Amors, there's a very red high density of objects in this part of the NEO population as well. So this makes it a little bit easier to actually be able to see how many points get piled up at these different major axis versus eccentricity values. Oh, I see another chat question. Okay, more conversations. I will let that conversation continue in the chat, and I'll keep going through this so that we can try to get to the end before we get to the top of the hour. One other very quick thing is that if you want to also be able to compute the fraction or the percentage of the different of the number of objects in the different subpopulations out of the total population, that's also a very simple calculation, of course, to be able to run. And so you can look and see the percentage of the NEOs that exist in each of these different subpopulations. Okay, so let's see. What if we also wanted to talk about the terrestrial planet crossing regions for terrestrial planets other than just the Earth? And so here we can also get the planet crossing curves for Mercury, Venus, and Mars, just the same way as we did for the Earth above. So we're going to do that. And then here we're going to plot all of the terrestrial planet crossing curves on a semi-major axis versus eccentricity plot. So the blue curves here, again, are Earth crossing space. So everything between the 2 blue curves are Earth crossing semi-major axis versus eccentricity values. Same thing for the red curves. Everything between the 2 red curves are Mars crossing orbits. For yellow, this is Venus, and green, this is Mercury as well. And then next we could also plot, so now we've got the planet crossing curves for these planets. We can also plot our NEO populations on top of this as well. So we're going to put our 4 NEO subpopulations. We're also going to put the planet crossing curves for each of the 4 terrestrial planets, and we'll add our annotations to label the different NEO subpopulations on here as well. So we're kind of going to put all of this together here. So this kind of goes back to the conversation that was just happening. So here in between the 2 red curves, this is Mars crossing space. And so you can see that most of the Amors and even most of the Apollos and even some of the Attons are actually on Mars crossing orbits. And so if you look at the outermost curves here, I guess this 1.3 AU NEO defining curve for the perihelion distance, this curve here is something that has an aphelion at the perihelion of the Earth, which is a confusing way to think of it. But this is the perihelion curve for the Earth at 1 AU, and here's the perihelion curve for Mars as well. So this 1.3 AU curve sits pretty much right between the Earth and the Mars curve here as well, which kind of goes back to your question before, Valerio, as well. Okay, I think I saw something else pop up in the chat. Okay, great. All right. So let's see. We could also split up the NEOs into populations of planet crossing NEOs. And so rather than splitting them into the traditional NEO subpopulations, you could simply extract all of the Mercury crossing NEOs, for example, and you could do this for all of the different planets. So if we go ahead and run this as well, we're going to make a 4-panel plot, again, showing the semi-major axis and eccentricity distribution. But now, rather than splitting these NEOs up into the different subpopulations, we're just looking at the populations of NEOs that cross a given planet. And so in the top left, these are all of the Mercury crossing NEOs. You can see that they don't really fill all the way down on the very inner edge here. This is probably partly observational bias from the known population, but there also just aren't very many NEOs that get all the way down this very, very inner part of the solar system. The top right are all of the Venus crossing near-Earth objects. The lower left are the Earth crossing NEOs, and lower right are the Mars crossing NEOs as well. So this is an example of how you could pull out all of the objects that cross the orbit of a given planet if you wanted to be able to do that. Okay, I'm going to skip down here a little bit. You could also extract the planet crossing NEOs for more than one planet or all of the planets together. So say we wanted to get both the Venus and Earth crossing NEOs, or we wanted to get the NEOs that cross the orbits of Mercury and Venus and Earth and Mars. So we could also extract those populations, and then we could make a plot of them as well. So this is going to be an example of plotting the semi-major axis versus eccentricity for all of the Venus and Earth crossing NEOs together. And so here we have all of the planet crossing curves still on this plot, but we're looking at all of the NEOs that happen to be both Venus and Earth crossing. So they're between this inner blue curve and between the outer yellowy orange curve on here as well. Okay, so we've got a few minutes left here. One more orbital parameter that we haven't talked about. So all of this has been covering semi-major axis versus eccentricity for the NEOs. There's lots of interesting things that you can plot just looking at those 2 different orbital elements. But another interesting orbital element that we can look at as well is the inclination, which is the tilt, the angular tilt of an orbit out of the plane of the solar system. And so let's go ahead and make a plot, a scatter plot of the semi-major axis versus inclination, going up to an inclination of 90 degrees. For all of the NEOs, we're going to do a 2-panel plot. So we'll put the semi-major axis versus inclination on the top, And then we're going to put our semi-major axis versus eccentricity scatter plot on the bottom again. That was the very first plot that we made. So on the bottom, this is the first plot that we made of semi-major axis versus eccentricity for the NEOs. And then on the top, we've got the semi-major axis versus inclination up to an inclination of 90 degrees. And so you can see how this third orbital element also compares to these other two. Again, sometimes it's difficult with these scatter plots to really be able to see the density of all of the points that we know are piled on top of each other in these plots. So we could also do the same thing here with this hex bin function as well to get this two-dimensional scatter plot for these three orbital elements as well. And so you can see the inclination distribution here and where this large overdensity of points exists in semi-major axis versus inclination point as well. Bob, you raised your hand.
On the previous plot, the vertical lines, is that a software artifact?
At 1AU here?
Yeah, and then at 1.6 AU?
Oh, and here as well. Yeah, that very
That
well
Earth
might
and
be
Mars?
a sampling effect from trying to create these orbital catalogs.
Okay.
Valerio.
That's possible, but they can also be resonances with Earth and Mars. 1OU, you have this orbital region. So you will have one-to-one resonance with Earth. Some object will be captured, but the majority will be lost. So you will see a drop like the Kirkwood gap in the main belt. And I think the other one is about 1.52, which should be with the orbital of Mars. So this might be real, but we need to check it.
Right. Yeah, there are absolutely resonances that can exist in here, and especially on a semi-major axis versus eccentricity plot, they appear as these vertical lines, these mean motion resonances. The weird thing about this is that they also are shown as kind of vertical lines in the semi-major axis versus inclination plots, and the resonances don't follow that kind of pattern in AI space as well. And so that leads me to think that this might be more something to do with how the simulations were put together to construct DP 0.3, since they're in both the eccentricity and inclination distributions. But yes, it is kind of noticeable, especially at 1AU, that there's this kind of drop off in the number of points at 1AU. So, but maybe that's somehow an observational bias effect for the Rubin simulator that was used to put together DP 0.3. I'm not sure. Okay. Let's go ahead and keep going. We've got just a little bit more to go here. Okay, so we've looked at the two-dimensional histogram plot here. We can also look at the another two-panel plot here that again has semi-major axis versus eccentricity on the bottom and semi-major axis versus inclination on the top. But we can split up the four different subpopulations again so that we can see what the inclination distribution for the different subpopulations looks like. So if we go ahead and run this cell as well, again, this bottom plot should look familiar from the one we made above. And then on the top here, we've now also overplotted the four different subpopulations in inclination space as well. And you can see there's a lot of overlap between the Amors and the Apollos in their inclination distributions, and the same thing for the Attens and the small number of Atiras that are on here as well. Let's see, I think I'm gonna go ahead and skip this and move on a little bit. Okay, so one final thing. So far, we've only been plotting inclinations up to 90 degrees, which is an orbit that is tilted perpendicular to the plane of the solar system, but it is possible for inclinations to go all the way up to 180 degrees. And so typically anything that has an inclination between 0 and 90 degrees, we say that it's on it's often a normal orbit, but it's a prograde orbit where the motion is going in the same direction as everything else in the solar system. Essentially, once you get up to 90 degrees and beyond, if you project an orbit's motion down into the plane of the solar system, it is then going contrary to the motion of everything else. And so we call this retrograde motion. So we have retrograde inclinations ranging from 90 to 180 degrees and prograde inclinations from 0 to 90. So we can extend our inclinations all the way up to 180 now and make another scatter plot here. So this is just the semi-major axis versus inclination, but we've put a dashed horizontal line here that will distinguish between prograde inclinations and retrograde inclinations up on the top here above 90 degrees. And we see that there are actually a small number of objects in the DP 0.3 catalog for the NEOs that have these very high, rare orbital inclinations. Now, since there's only a few of these objects here, we can actually extract them directly from our data set here and just select the objects that have these inclinations larger than 90 degrees. And we can even just print them out. There are 6 of them here. If we're interested in looking at them individually, these are clearly outliers in the population. So something that would be interesting to look at once LSST is producing actual data. Here we see that the first one listed here is 2009 HC. It's 8. It's supposed to be 82. So that is a mislabeling here in the MPC designation for the catalog. This is a real known asteroid that's on an orbit with a very high orbital inclination of 154 degrees. And then the rest of these are simulated objects. This is a simulated long period comet. And then we have 4 simulated interstellar objects that are in the catalog here as well. And I think this is the very last plot here. Since there's only 6 of these, we can also do a scatter plot of their semi-major axis versus inclinations, where we're just restricting our inclinations to the retrograde region. And we can even label them on the plot with their specific MPC designations so that we can tell which object is actually which on this plot as well. So I'm going to go ahead and run this cell. And we'll look at this plot here. So again, this is semi-major axis versus inclination from the 90 to 180 degree range. And these are the 6 retrograde NEOs that are in the DP 0.3 catalogs. We can see that all of the interstellar objects that were simulated in the catalog have semi-major axes less than 1. The long period comet is over here with the largest semi-major axis, which is what you would probably expect. And then here is 2009 HC82 as well, which is the one real known asteroid on a retrograde orbit. Okay, so that is the end of this notebook. We're very close to the top of the hour, but we do have a few more minutes for some questions, if there are any more questions as well.
I have kind of a boring question. I saw you've been using HexBin, and I've been using HIST 2D, and I was wondering, is there an advantage of HexBin that you know?
Oh, I'm not sure if I know what the difference is.
Okay.
If
Okay,
there's a specific difference between the two.
I'll just check it out. It's a really great talk. It was weird to pick out that little thing, but I was wondering. So thanks.
Yeah, thank you. Douglas, go ahead.
Well, just in response to Bob, I've used both. I'm not sure there's a big difference. I think HexBin comes directly out of pandas, maybe. I'm not sure. So if you're doing a pandas data frame, it's easily just do a HexBin, but maybe I'm not 100% sure. Oh no, this you just do it from the axis. Yeah, I don't know. I've used both. HexBin's kind of nice, but sometimes there's a normal 2D heat map is good too.
Yeah, I'm not sure. But thanks, Doug. Okay. Oh, yes. Thank you, Sean, for pointing out in the chat that there is a warning about the truncated designations. It's a known issue with the DP 0.3 simulated catalogs that there are objects that have truncated designations, such as this example that we saw of 2009 HC82 only being listed as 2009 HC8. So it's a known issue that will hopefully be able to be remedied in the future. Yes, Valerio.
Well, thank you. It was a very great talk. Just a very simple question. Do you know if there are other objects that are known by inclinations or other than these 2009 HC82? I never. This was the first case that I know of, so I was just curious.
Sorry, what was the first part of your question? How are
If there are
there
other asteroids that are known to be other NEAs that are high inclination, that are retrograde.
Are there others that are known? I think that 2009 HC82 is the only known asteroid to be on a retrograde inclination. There are other objects like the Damocloids, which are these thought to be now extinct comets that are on asteroid-like orbits but don't have any evidence, any cometary evidence of activity anymore. And so there's a small number of objects that and some cometary type orbits, because near-Earth objects aren't just asteroids, they can be comets as well. There are some cometary type orbit or objects that have these retrograde inclinations, but I think 2009 HC82 is the only object that is believed to be an asteroid that is actually on a retrograde orbit. So they are very rare indeed, but from some of my past research, I think that these retrograde asteroids can actually get on these orbits through resonant type of mechanisms that you were talking about before with these mean motion resonances that can interact dynamically with the objects and be able to get them onto these retrograde inclinations. So it's not easy for these objects to get there.
Thank you.
Yeah. Oh, and Sean says in the chat that there are some other retrograde NEOs, but they have larger semi-major axes than we actually show here. So they were cut off in these plots. Thanks for that, Sean. All right, well, we are at the top of the hour. If there are no more questions.
This was amazing. Thank you.
Yeah, well, thank you so much, everyone, for coming. And remember, there's no Rubin Science Assembly next week, but please come back in 2 weeks if you're able to hear Valerio tell us about asteroid taxonomy with DP 0.3. So I hope to see you all then.
This was worth watching twice.
Well, thank you.
It was really good. Thank you.
Thank you.